Hi everyone, welcome to chemistry. In chemistry we're studying matter and how it changes, and to do that we often are making very precise measurements of the matter and how it's changing. So we need to have a pretty good grasp of how to make measurements, what the units are. We talked about that a little bit, and you guys have already done a lab where it was important that you were both accurate and precise. But I want to get a little bit more in depth on that and focus on how we know if a measurement is accurate, if it's precise, and what the difference is. So if we take a look at measuring, different measuring devices have different degrees of precision, and all I mean by that is they have different numbers of divisions on them, and so those divisions determine how many decimal points we have in our answer. The more decimal points we have in our measurement, the more precise it is. But we can always estimate one more place than our measuring device actually shows, and those digits that we include in our measurement are called significant digits. Significant meaning they're valid, they count, they mean something, they have value. So let's take a look at an example. This is a decameter ruler. So from here to here, from the 0 to 1, that's 1 decameter. That's the equivalent of 10 centimeters or 100 millimeters. Okay? Now if all I have is a ruler that's marked off in decameters and I try to measure something like this blue block here, how close can I get? Well, I know it's less than 1. I know it's probably more than 0.5, somewhere in between 0.5 and 1, and so I'm going to go with 0.6 decameters. Is that exact? Well, it's exact to the 0.6. That's estimated. I know it was less than 1. I know it's more than half. So this is a significant digit, but I can only go to this one decimal place because I don't have enough other divisions on my measuring instrument. I couldn't say if it's 0.55 or if it's 0.65. Those don't make sense. Those are guessing. Okay, this is a good estimate. It's 0.6. It's more than half. I think it's less than 0.7. I'm going to go with 0.6 decameters. Now, if we increase the precision of our measuring instrument, say we have more divisions on it, so instead of just 1 decameter, now I have centimeters. I've taken my 1 decameter, which is right here, and I have divided it up into 10 places. Now if I go to make that same measurement, I can be more precise because now I can see this is 6, this is 7, so I have a little bit more than 6. There's 6.5, so I'm going to guess this is probably 6.3. But now I'm in centimeters, and if I go back to decameters, then I just move this thing that direction, which is 0.63 decameters. And so you can see I've added this second decimal, I've added that precision to my answer. And now if two people make this measurement, they'll both probably get close to 0.63. So if I increase the precision, I've increased the repeatability of this measurement. If I go even more precise, and now instead of dividing it up into 10 different measurements, I'm dividing it up into 100. So now I have a millimeter scale, and so 1 decameter here is 100 millimeters. Then when I make this measurement, I can get even more precise, and so now I can see that my measurement up here, 0.63, was a little bit off because I have 0.61 or 61, 62, 63. There's 64, and I'm going to say it's just before that 64. So I would say that this is 63.8 decameters, or sorry, 63.8 millimeters. My scale changed to millimeters, which is 0.638 decameters. Now, I've went from having 1 decimal point, the 0.6, to having all 3 decimal points. I've increased my precision because I've increased the divisions on my ruler, and the more I do that, the more divisions I can get, the more precise I can get, which means the more times this measurement's made, the more times it's likely to come up the same. If you're just given a measurement, it's sometimes hard to tell if every digit in it is significant. So let me give an example. Okay, so why wouldn't everything be significant? Sometimes we are just locating where the number should be. Like if I have something that's only 10 centimeters long, that's the same thing as saying 0.1 meters. Or if I had something that was 1 millimeter long, that's the same thing as 0.001 meters. So what do these zeros do? Well, they're not in this measure, but these two things are equivalent. These zeros just indicate that this is 1,000th of a meter. So they're place holding zeros. They're not value holding zeros. So it's only if something has a value that we include it as significant. So these zeros, they hold the decimal place out over here. So we could have rewritten this as 4.5 times 10 to the negative third. And we can see that 4.5, that is significant. If we look at another example, 450 grams, this is ambiguous. If we want that 0, do we know that it's saying it's exactly 450, or is it actually locating this to tell me that this is hundreds, this is tens, this is ones? We're not really sure. We assume that that one is not significant unless there's something to note it. If you want it to be significant, you should write it like this: 4.50 times 10 to the 2. That's different than 4.5 times 10 to the 2 because this 0 is explicitly stated, yes, this is a 0 value, as opposed to here we're saying, yeah, well, you got to move the decimal place over 2 points, but we're not really sure if that second one counts or not. So it's not a significant digit. So this 0, we're going to say it's a locator. It serves to push this thing away from the decimal point. If we take a look at another example, this 12.30 liters, this 0 is significant, and that's because it trails this decimal point. That is, it's after a decimal point and after a number after the decimal point. So it's telling me it's not 12.31, it's not 12.29, it is 12.30. It is indicating the value of the hundreds place, otherwise, or the hundredths place. Otherwise, there would be no reason to put it there. One more example, 16.03 seconds. This is actually a value because it's between other significant digits. It's telling me, well, we're measuring all the way to the hundredths place. It just happens that we didn't quite make it to a tenth yet. So we have 16.03 seconds. Everything in here is significant. So the only thing you have to really look out for are these placeholder zeros. If it's locating a decimal point instead of indicating a value, it doesn't count as significant. Why does this matter? Well, we don't want to over-report our precision when we do arithmetic and mathematics. And so when you're doing arithmetic with significant digits, there's a couple rules. Addition and subtraction, the rule is pretty straightforward. We cannot be precise than our least precise measure. We can't be more precise than our least precise measure. So our final answer is rounded so its precision matches that of the least precise measurement. You'll notice this measurement right here is precise to the tens, hundreds, thousandths place. This measurement is precise to the tens, hundreds place. So that is our least precise measure. It's only got 2 decimal places of precision. So when we add this up, when we take 12.43 plus 1.055, we end up with 13.485 centimeters. But our final answer we won't report like that because we're not sure about this, so we can't be sure about that. We can only be sure to this place. That's a 5, so we're going to go up. So this becomes 13.49 centimeters. Okay, so we're only precise to the hundredths place because our least precise measure was only precise to the hundredths place. The rule with multiplication and division is a little bit different. Instead of looking at the least precise thing, we round it so that it's got the same number of digits as the least number of digits. Okay, so what that means is this thing right here has 3 significant digits in its measurement. This has 4 significant digits. We're going to use this one. Our final answer is going to have 3 total significant digits. So when we take 71.25 divided by 32.1, we get 2.219626 grams per milliliter. Don't forget your units when you do this division. They just divide. But we can't report that much precision. We can only have 3 numbers, 3 digits in our final answer. So we're going to go with 2.2, and then this 196, that's going to round up to 2. So 2.22 grams per milliliter. And that has the same precision as our least precise number in multiplication and division. Now, when you're doing math with units, I briefly touched on this, you have to be sure that if you're adding and subtracting, units must match. So if you're going to take 12 milliliters plus 13 milliliters, you're going to get 25 milliliters. But if you're going to take 10 centimeters plus 2 meters, they have to match first. So you have to do that conversion. So 10 centimeters is 0.1 meters. So 0.1 plus 2 equals 2.1. Now if these were both in significant digits, you'll notice this is only precise to the ones place. This is a tenth of that. And so I would have to actually round my answer back to 2 meters in order to keep my precision in significant digits. Okay. Now, when you do multiplication and division, the units don't have to match because, okay, well now let me put a caveat on that. The units don't have to match if they measure different quantities. Like it's impossible to add seconds plus meters because this describes a distance, that describes a time. They're not the same thing. You can't add them. It is possible to take meters and divide it by seconds. That's a ratio. It describes the rate of change of position. But if you're taking meters times centimeters, you shouldn't, because these both measure length. You should make them both the same unit. You can change meters to centimeters or centimeters to meters. When you do that multiplication and division, those should match. But if we have two different units, two different quantities we're measuring, then the units are combined as algebraic quantities. And you guys have done that before. If you drive 12 meters in 3 seconds, then you're moving at 4 meters per second. So that's a derived unit. It includes both. The density you guys calculated, 16 grams divided by 4 milliliters. That is 4 grams per milliliter. So that's not so bad. All right. Then it comes to actually reporting accuracy and precision. So precision depends on your measuring device, how many divisions it has, how repeatable your measurement is. Accuracy depends on how close you are to the real value or how close you are to the true value. Oftentimes we can look this up in an index, in a handbook somewhere. The periodic table is often used for our true values because it lists the density of lots of different elements. It lists their atomic mass, so we can use those values. And those values come from hundreds of measurements that have been averaged over thousands of times. So we have a pretty good idea, yes, this is the true value. Now, we calculate accuracy using a thing called percent error, which just tells us how different a measurement is from what it should have been. So this is the formula. Measured value minus true value, that's an absolute value, we don't care if it's positive or negative, divided by the true value times 100%. So say you measured the density of gold to be 17.9 grams per milliliter, and then you go look it up and you see that it's actually got a density of 19.3 grams per milliliter. How far off were you? Well, you could say you were off by 2.6 or whatever that works out to be. You could subtract and find the difference, but that's not necessarily a big deal, right? If you're measuring a football field and it's 100 yards long and you're off by 3 feet, no, let's say yard, it's not a big deal. But if you're measuring the length of a person and you're off by 3 feet, that's a big deal. So percent error gets rid of that, well, was it a big measurement or a little measurement? It just compares how wrong you were to what you should have been. So it makes it a percent difference instead of an absolute difference. So if I wanted to do this one, I would take 17.9 minus 19.3, absolute value, so I don't care that that's going to turn out negative, divide it by the 19.3, the true value, and then multiply it by 100% just to make it a percent. So 17.9 minus 19.3 is 1.4, divide it by 19.3, and I get 7.25, or 0.0725, so multiply it by 100, and I get 7.25%. So that tells me I was within 7.25% of where I should have been, which actually isn't that great of accuracy. We hope to see things around or under 5% when we're making measurements. If we're doing a good job, that should be obtainable most of the time. Now, the true value might not have been just one value. It might be the average of 6 or 7 measurements that you've taken. Sorry, not the true value. The measured value might be an average of 6 or 7 measurements you've taken, and doing that average helps you eliminate error, which is all that says down there. All right. Now, precision is a little bit different. Remember, I said precision is repeatability. Basically, it describes how spread out your measurements are. If you take and you measure something, and all your measurements fall in a range, like if you're trying to measure something and its actual value is 10 millimeters, and you measure something between 9.8 and 10.2, but most of your measurements are in here, that's fairly precise. But if you measure between 9.1 and 10.9, and all your measurements are spread out over this big long distance, that's not so precise. You have no repeatability there. So there's actually a way to define precision, to calculate precision, repeatability of a measurement Each time you measure something, you should come up with the same value, and that spread of your values is how precise you are. The closer the individual values are to each other, the more precise the measure, and the range, which you guys looked at before, is one indication of precision. The smaller the range, the more precise you are. But there's another thing called standard deviation, and you guys have probably heard of this before. It's a measure of precision, and basically it tells us how close measurements are to each other. It's got sort of a complicated formula. We're going to take a look at it. Okay, variance, which is the first step in getting standard deviation, and standard deviation. This right here is the formula for variance. Sigma squared is variance. This giant sigma, this is the sum of, x is a measure, mu is the mean, square means square, and n is the number of measures. That doesn't make any sense. Let's take a look at it. Okay, so this says sigma squared is variance, mu is mean, n is the number of measures, square root of variance is standard deviation. I'm going to show you how this all works, then I'm going to show you how your calculator does all the work for you. Alright, so here's a table of data I just made up. Okay, so I have all these different measurements, 12.3, 12.8, 12.4, 11.9, 13.1, 12.6. I know they're just numbers because they have no units, but we're getting there. I don't know, if I was measuring the same thing every single time, I should have come up with the same number every single time. And you can see I didn't. I've got 13.1, 11.9. Those are two pretty far apart numbers, and lots of 12s in the middle. So what we do first with all those different measurements is we find their average. Remember, average is the sum of each measure, so the sum of x, divided by however many there were. So I would take 12.3 plus 12.8 plus 12.4 plus 11.9 plus 13.1 plus 12.6, and I would divide that by 6 since there's 6 measures. I've already done that math because I'm lazy, and that turns out to be 12.517. Now, that is mean. Okay, so this is equal to the mean, which is mu. Okay, you guys won't ever have to know this, but that is the mean symbol for statistics. Now, if we were actually to just take the measurement minus mean, that would tell us how far the measurement lies from the average value. That's all this tells us. This one tells us that our measurement is 0.217 units below our value. This one's 0.283 units above our average value. 0.117 units below, 0.617 units below, 0.583 units above, 0.083 units above. But because the mean is right in the middle of all the values, these are all going to sum up to 0, which doesn't help us tell how far apart they are at all. So to get rid of all those negatives and positives, we square these numbers, and that makes them all positive. And then we add them all up. I didn't add them all up because I don't care what that is, but that's what this symbol means. We're going to sum the square of all those things, and then we're going to divide it by how many there were. So we're going to divide the sum of all these numbers by 6, and that gets us the variance. Then if we square root the variance, so the square root of sigma squared, which just gives me sigma, is called standard deviation. Now, the reason I don't have to do all this math is because your calculator can do all this math. Let me show you exactly what I mean. Alright, so I'm looking at the home screen of my calculator, and first thing I want to do is I want to put in that list of numbers that I had. And that list of numbers is right here. Here's all the measurements under my measurement column. So 12.3, 12.8, 12.4. So what I do is I push statistics. That's the stat button here, because when we find the average of this, that's a statistic. And I'm going to say edit. I want to edit where my statistics are. Now I have lists in here already. These are lists of numbers. I don't care what they are. So I'm going to arrow over to L1, arrow up to that, and I'm going to push clear. And that's going to clear all the data right out of L1. And now I can just type in my measurements on my calculator. And so that's 12.3, 12.8, 12.4, 12.3, enter. 12.4, enter. 12.8, enter. I gotta go back to my list. 12.3, 12.8, 12.4, 11.9, 13.1, and 12.6. 11.9, 13.1, 12.6. So now I have all 6 of my measurements in the list of my calculator here, and now my calculator can do all that math for me. I'm going to push second quit to get out of this, and then I'm going to tell it to do some math. So I push the statistics button again, but now I'm going to arrow over to do some math, some calculations. And I want one variable statistics, which is the first thing, and I've got to tell it where the numbers are I want it to compute statistics on. So I push second L1, which tells it to do this on L1, that list we just entered, and then I push enter, and it gives me a whole bunch of things. This first value right here, this x bar, that is the mean value, so that's the average. Okay? This sigma x, that is the sum of all the measurements. Sigma x squared, that's the square of the sum of all the measurements. This right here is what I really care about. This is the small sigma x. This is the standard deviation of my measurements. Now, that's 0.380. What that means, if I come back to my PowerPoint, 0.380 is my standard deviation. Whoops, go back one. Okay, if I have 0.380 for sigma, 0.380 equals sigma, that tells me the majority of my measurements are plus or minus 0.380 units from what I actually had as a mean. So 12.517 I believe was my mean. The majority of my measurements are between 12.517 plus or minus 0.380. So that has sort of an indication of the spread of my measurements. Is this real precise? No, not really. The smaller this number is, the more precise it is, but that does tell me the majority of my measurements lie between probably 12.1 and 12.8. Okay, which is a pretty good spread. We would hope to see something a little bit better than that, but that standard deviation does tell me how precise my measurement is.